How fast can I explain the basics of mechanical engineering? We're about to find out. So it's really important to understand the relationship between physics and calculus. Right here is the derivative power rule, and notice I have a worked out example here as well. Now these derivatives will also be applicable in physics, where the derivative of your position with respect to time is velocity, and the derivative of velocity with respect to time is acceleration. We can visualize this by looking at three graphs, where the graphs represent position, velocity, and acceleration. Now let's say I have this function, which represents position. So in this case, I can plot this function on this position graph right here. Notice here that I have a linear function with a slope of 2, and that matches the function that we have. Now what I'm going to do is take the derivative of this function using the power rule we saw on the previous page. Taking this derivative, I should end up with 2, and this is going to be the velocity function since the time derivative of position is velocity. Now notice here if I plot this function on our velocity graph, it's just going to be a constant value. Since we got a constant value of 2 right here, it's going to constantly be 2 on our velocity graph. Now what if I take the derivative of this velocity function, which is also the second derivative of position with respect to time? I'll end up with the derivative of 2, and 2 is a constant number. Anytime you take the derivative of a constant, you're going to end up with 0. So our acceleration is going to be 0 meters per second squared, meaning we don't have an acceleration in this system. So let's apply this knowledge to a pulley system. So let's say we have this pulley system right here, and we have the two weight forces approximated for us. Now what I'm going to try to calculate is the acceleration of the system, and I'm going to use Newton's second law to calculate this. So first I'm going to take the mass and divide it by both sides. That'll get the mass to cancel, giving me that acceleration is net force over total mass. Now the net force is going to be this 40 Newton force, which is the driving force, minus this 20 Newton force, which is opposing. So I'm going to end up with 40 minus 20. And something I forgot to mention is we can assume that there's no friction here, or that the friction is so small that it's negligible for this problem. So we have 40 newtons minus 20 newtons, and then we need to divide this by the total mass, which is just going to be the combined mass of these two objects right here. So we'll have this fraction right here, and evaluating this on a calculator, you should get approximately 3.28 meters per second squared. So this right here is your acceleration. You could also say that this is your derivative of velocity with respect to time, or your second time derivative of position. Now I want to explain the effectiveness of pulley systems in mechanics. Now notice if we just have a very simple pulley system, we'd have to pull with the same force that the weight force is exerting down. So we have a 200 Newton weight force, and we'd have to pull with 200 newtons as well. So this is not a very effective pulley system. But what if I rearrange this pulley system to look something like this? Well, now the tension is actually going to be split between the two sections of rope we have right here. So what I'm going to end up with is a tension force of 100 newtons acting on each position of the rope here. So that means we only have to pull with 100 newtons of force. Even though we're pulling with less force, we actually have to pull with greater displacement of rope down, because now each of these sections of rope are going to be pulling up with 1 meter. So that means we're going to have to equate that by pulling 2 meters of rope down in order to move this up 1 meter. Likewise, if you wanted to pull the block up 2 meters, you'd have to pull the rope down 4 meters, so that way the work stays conserved. So that was a basic introduction into mechanical engineering.